The atomic interaction simulation is an innovative educational tool designed to help students understand the fundamental principles governing the interactions between atoms. This simulation allows students to investigate how the relationship between attractive and repulsive forces influences atomic behavior. By providing a visual and hands-on approach, the simulation enhances students' understanding of the Lennard-Jones potential and the van der Waals radius. The simulation focuses on the principles of interatomic forces, which are crucial in understanding the behavior of atoms and molecules. It illustrates how the balance between attractive and repulsive forces determines the equilibrium distance between atoms. The simulation includes various tools and visual aids to help students explore these concepts in depth. The interaction between two atoms is modeled using the Lennard-Jones potential, which describes the potential energy of interaction between two non-bonded atoms or molecules. The simulation includes a graph that displays the potential energy as a function of the distance between the atoms. This graph allows students to visualize the Lennard-Jones potential and understand the relationship between attractive and repulsive forces. The simulation allows students to adjust the parameters of the Lennard-Jones potential and allow them to observe the resulting changes in the potential energy graph and the behavior of the atoms. The atomic interaction simulation provides a hands-on approach to exploring the principles of interatomic forces. By adjusting the parameters of the Lennard-Jones potential and observing the resulting changes in the potential energy graph and the behavior of the atoms, students can understand key concepts such as balance of forces, Lennard-Jones potential, and potential energy graph. The interaction between atoms is governed by the balance between attractive and repulsive forces. The attractive forces pull the atoms together, while the repulsive forces push them apart. The equilibrium distance between the atoms is determined by the point at which these forces are balanced. The Lennard-Jones potential describes the potential energy of interaction between two atoms as a function of the distance between them. The potential energy is a combination of the attractive and repulsive forces, with the attractive forces dominating at larger distances and the repulsive forces dominating at smaller distances. The potential energy graph displays the potential energy as a function of the distance between the atoms. The graph has a minimum at the equilibrium distance, where the potential energy is the lowest. This minimum represents the most stable configuration of the atoms. The atomic interaction simulation offers several educational benefits. The simulation provides an interactive and engaging way to learn about the principles of interatomic forces. Students can actively participate in the learning process by adjusting the parameters of the Lennard-Jones potential and observing the resulting changes in the potential energy graph and the behavior of the atoms. Interatomic forces and the Lennard-Jones potential can be abstract and difficult to understand. The simulation provides a visual and tangible representation of these concepts, making them more accessible and understandable. Students can experiment with different parameters of the Lennard-Jones potential and observe the resulting changes in the potential energy graph and the behavior of the atoms. This exploratory approach encourages critical thinking and problem-solving skills. The simulation provides a practical application of the principles of interatomic forces, which are fundamental to many real-world phenomena, such as the behavior of gases, liquids, and solids, the design of materials, and the study of chemical reactions. This helps students see the relevance of these concepts in everyday life. The simulation introduces students to the process of data collection and analysis. By observing the potential energy graph and the behavior of the atoms, students can collect data and analyze the relationship between the parameters of the Lennard-Jones potential and the equilibrium distance between the atoms. To implement the atomic interaction simulation in the classroom, teachers can follow these steps. Begin with a brief introduction to the concepts of interatomic forces, the Lennard-Jones potential, and the van der Waals radius. Provide examples to illustrate these concepts and explain how the simulation will help students understand them. Demonstrate the simulation to the class, showing how to adjust the parameters of the Lennard-Jones potential and observe the changes in the potential energy graph and the behavior of the atoms. Explain the importance of observing the balance between attractive and repulsive forces and how it relates to the principles of interatomic forces. Allow students to explore the simulation in small groups or individually. Encourage them to experiment with different parameters of the Lennard-Jones potential and observe the resulting changes in the potential energy graph and the behavior of the atoms. Provide worksheets or prompts to guide their exploration and data collection. After collecting data, have students analyze the relationship between the parameters of the Lennard-Jones potential and the equilibrium distance between the atoms. They can use the principles of interatomic forces to interpret the data and draw conclusions. The atomic interaction simulation is a valuable educational tool that brings the principles of interatomic forces to life through an interactive and engaging context. By allowing students to investigate how the relationship between attractive and repulsive forces governs the interaction between atoms, the simulation provides a hands-on learning experience that enhances understanding of these fundamental concepts. This interactive approach not only makes learning more enjoyable, but also fosters critical thinking, problem-solving skills, and a deeper appreciation for the relevance of interatomic forces in the real world.